So today's class, if you've taken digital logic, I know some of you haven't taken digital logic quite yet. I know there's not a lot of people here, so, a lot of people aren't here. So who here has not taken digital logic or is currently taking it? So 2, okay. The rest of you can go to sleep. This is just a review of what you learned in digital logic. It's just going to be going over stuff that you've already covered in there. Starting with digital logic circuits. You can look at a digital logic circuit as a black box. You don't know necessarily how it's implemented, but you know if you give it certain inputs, it'll give you certain outputs. So, combination of signal bits, ones and zeros, can be transformed into other combinations of signal bits by means of various circuits. Because a variety of different technologies are used in construction, engineers and designers find it useful to think of logic gates as black boxes. How it's implemented doesn't really matter as long as it works the way it's intended. So take this black box. It has 3 input signals, 1 output signal. What goes on in the middle doesn't really matter as long as the input-output table is predictable. And it lists all the possible input signals together with their corresponding output. So for the 3 input, there would be 8 possible combinations of input. And the input-output table will give you the output for each combination of input. This is an example of what such a circuit might have as an input-output table. All right. These are very similar to truth tables. There's a subtle difference between the two. I don't remember off the top of my head what it is. But this is an input-output table, not a truth table. The ones can be considered correspond to true, and zeros correspond to false. So when you have a NOT gate, it is like an inverter. It inverts the input, like the NOT symbol on our logic statements that we've been covering so far. An AND gate is a circuit with 2 inputs and 1 output, like the AND logic operator. If both inputs are 1, the output is 1. Otherwise, it's 0. Otherwise, it's false or 0. OR gate is a 2-input signal device as well. It has 1 output. If both signals are 0, then the output signal is 0. Otherwise, the output signal is 1, just like the OR logic operator. So here's the symbols used in circuits for the AND, OR, and NOT, and their input-output tables. Yeah, it's just another symbol to memorize for the various logic operations. Now, the rules for a combinational circuit is never combine 2 input wires. The reason being is, if you have 2 inputs coming in and joining, if one is high and one is low, you'll have a short circuit. Nothing will go to where you want it to go. It'll just short out, things will start smoking, and we all know smoking is bad for you. So No combining inputs. A single input wire can be split and go to two different inputs of two different gates, or two inputs of the same gate. An output wire can go to an input of another gate. And for combinational circuits, no output of a gate can eventually feed back into that gate. No looping back. That is done in sequential circuits, which are beyond the scope of this class. So we won't go into that. But input-output table for a circuit. If you're given a set of input signals for a circuit, you can find its output by tracing through the circuit gate by gate. So, inverse of P, invert P, ANDed with Q. If P is 0, after the NOT, it's a 1. Going into the AND gate, you have a 1 and a 1, because Q is 1. So the AND of that would be, of 1 and 1, would be 1. With this, you again work left to right. P or Q. P and Q are 1 and 0. So P or Q would be 1. Invert that to a 0. Input that into the AND gate with the R, which is a 1. So you have a 0 and a 1 ANDed together, and that is a 0. So you can see where you can trace, write down the input values at each step along the way until you get to the output. But you move left to right through the diagram. Likewise with the second circuit. Now the input-output table for the following circuit. That is, you all create a table like a truth table where you have 2 columns for the inputs, and a row for each combination. So 2 inputs, that's 4 combinations. And then you trace through the circuit for each combination. All right, and you get the resulting input-output table. Okay. Boolean expression corresponding to a circuit. In logic, variables such as P, Q, and R represent statements. A statement can have only one of 2 truth values, true or false. A statement form is an expression such as this, composed of statement variables and logical connectives. Any variable that can take only one of 2 values is called a Boolean variable, or bool in C++ if you're programming. An expression composed of Boolean variables and connectives is called a Boolean expression. That's what an if statement or a while statement takes, is a Boolean expression. It evaluates in the end to either true or false. Or in the case of circuits, 1s and 0s. So, find the Boolean expressions that correspond to the circuits below. In circuit diagrams, a dot indicates a connected wire. Where there is no dot and the wires cross, they don't actually touch. They don't mix the signals there. So, this is P or Q ANDed with the inverse of P and Q. This is P and Q ANDed with inverse of R. So here's my stylus. So this would be P or Q in parentheses because it's a gate and it's done to get together, ANDed with P and Q which is then inverted. And this is P and Q and R not. Yeah, I got that. You work left to right, constructing a gate with a gate is a single operation in parentheses. And this corresponds to this. This corresponds to this. This corresponds to this. And this corresponds to this. Make sense? Okay. Want to make sure everybody's on board. All right, so here is the way they do it out step by step. Trace through the circuit left to right, indicating the each output of each gate symbolically, and get the final result at the output. Oh, come on. Okay. A recognizer is a circuit that outputs a 1 for exactly one particular combination of input signals and zeros for all other combinations. These are very common in computers. You don't see them on the macro scale. You have to get into the micro, the architecture of the actual processor to see the recognizers. But you have the input-output table for the recognizer has results being zeros, except for 1, 1. Okay, and you can find the Boolean expression for that by didn't it? Oh yeah. You can, by looking at the input-output table that you want, you can construct the Boolean expression that corresponds to that one output being true and the rest being false. P and Q are high, and R is low, or 1, 1, and 0. So P and Q and not R. And the rest are zeros. All right. The circuit corresponding to a Boolean expression. It works the opposite as doing it from a circuit to a Boolean expression. I mean, a Boolean expression to a circuit they're opposites. So constructing a circuit from a Boolean expression or to a Boolean expression is done right to left instead of left to right. And you work from the outermost operation to the innermost when it comes to parentheses. So you have the outermost operation, the OR gate. We'll draw the OR gate. That's your output. And leftmost, what's that? Q inverted. So invert, and that goes to Q. And then here in parentheses, the next step in from the as far as parentheses is concerned is an AND operation. So that's an AND going into the OR, and it's an invert of P and Q. So we'll just do Q here. So you work from the outermost operation to the innermost, and you work right to left instead of left to right. So this is just a series of AND gates, making a 5-input AND gate effectively. I won't go through that one. But let's see here. Yeah, write the input variables in a column on the left side. Last operation executed when evaluating is an OR gate. Extreme goes to the extreme right. One input in this gate is the not P and Q. So the AND with the inverted input of P, and so on, as I went through and showed here. But and the P, Q and R and S and T are just AND gates feeding into one another down the line, which effectively makes a 5-input AND gate. Now, finding a circuit that corresponds to a given input-output table. Say you have an input-output table that you want these outputs given those inputs. So you identify which rows have a high or 1 for an output, 1, 3, and 4. And for each row, construct an AND expression that produces a 1 for that exact combination of input values and a 0 for all other combinations. So for row 1, P and Q and R, we'll do that. In row 3, P and not Q and R, we'll do that as well. And for row 4, P and not Q and not R, we'll do that. Then you link these AND operations together with OR operations, because you want it to be a high output for the high output on row 1, or the high output on row 3, or the high output on row 4. So you have ANDs in parentheses with ORs between them. Okay. Now this is called, this is the circuit diagram for it, assuming you have three input AND gates available and a 3-input OR gate available. By constructing those individual units and then individual sections, individual terms. Oops. And then ORing them together in the to produce the final output. Okay. Now, in digital logic, the symbols being used are going to be the multiplication and addition. So this form is called, in digital logic at least, the sum of products, because you're summing up these individual products. In math circles, they call it the disjunctive normal form, which is not as descriptive as the sum of products, I don't think, at least not in my opinion. But in digital logic, you'll see it referred to as the sum of products form. Simplifying combinational circuits. Consider the two circuits shown here. Are they the same or are they different? Well, if you look at if you trace through the circuit A, you'll find that its input-output table is right here, which is the same input-output table for an AND gate, which was the second circuit. Thus, the two circuits are the same functionality. Two the digital logic circuits are equivalent if and only if their input-output tables are identical. So they, you want to do the more simple version because it would take up less space and require less power and be cheaper and more efficient and all that fun stuff. So you want to reduce it down to its most basic level. So now to reduce it, you can do the input-output tables and for the complex circuit and try to find that way a more simple circuit for what you want to do. Or you can convert to your Boolean expression and then use the laws that we learned last time or in a previous lecture. Use the distributive law, then the commutative law, then the negation law, then the identity law. And you've used what's called Boolean algebra to demonstrate and simplify this expression is equivalent to that expression, and therefore a more simple circuit. Let's see here. Yeah, it follows that the truth tables for those two expressions are the same. Therefore, the input-output tables for the corresponding circuits should be the same, and the circuits are equivalent. NAND and NOR gates. NAND and NOR gates are kind of different. A NAND gate is a single gate that acts like an AND gate followed by a NOT gate. A NOR gate is the equivalent to a OR gate followed by an inverter. So the input-output tables are the opposite of the AND and OR gates, respectively. In math logic, the NAND is expressed with the Sheffer stroke and the downward pointing Pierce arrow for the NOR gate. These are the symbols for them. The NAND gate looks like an AND gate, but it has a little bubble. The little bubble indicates that the output is inverted. So it is an AND gate, but the output is inverted. Likewise, the NOR gate is an OR gate with the bubble indicating an inverted output, and therefore it is a NOR gate. And these are the input-output tables for them. You can see that these are the opposite of the AND and OR. The bits are flipped. Come on. Use theorem 2.11 and the definition of Sheffer stroke to show that P NANDed with P is the inverse of P. So if you look at P is it would be all the combinations of P and P is it would be 1 and 0, and so it would be 1 and 0. What's the output? Would be NANDed P 1 NANDed with P is a 0, and a 0 NANDed with 0 is a 1. So therefore, it equals to not P. So a single NAND gate can be used as an inverter by tying the two inputs together. All right. I won't go through the whole schmeal with this one, but basically the same thing can be true of an OR gate being expressed by using NANDs. That's what that circuit would look like over here. And that is the equivalent to an OR gate. So we have an inverter here. And we know that a NAND gate is the same as a AND gate with an inverter on it. So a AND gate would be an AND gate with an inverter on it. So this is a NOT, and OR. Your three basic gates can be constructed just using the NAND gate. That makes the NAND gate a universal gate. You can do anything, you can express any logical combination, digital logic combination, using just NAND gates. May take a little work, however, but it is possible. It might take a few more gates, but it is possible. Likewise, the NOR gate is also a universal gate. I will not get into the diagrams of the NOR gate being shown as a universal gate are not covered by the slide, so I'm not going to worry with them right now. Worry you with that. But here's how you derive the equivalence between the OR and the NAND gate implementation, and the inverter with the NAND gate implementation. And that is it for this. And we'll go to the next one. And for those of you who have had digital logic before, you thought the review was over. You are wrong. This thing has not been cooperating with me today. Come on. So, number systems and their circuits for addition. All right. Binary representation of numbers. Any integer greater than 1 can serve as a base for a number system. In computer science, binary notation is used because in modern electronics, not always, but most cases, the signals are one of two states, 1 or 0. There's a third one, but that's a technicality you'll get into later on in electronics or something. Anyway, derive the binary notation of the integers from 1 to 9. So, with binary, you only have 2 digits, 0 and 1. When you count in decimal, you only have 10 digits. So what do you do when you reach the top of the top value digit in a column? Yeah, it starts over again, and you add 1 to the next column. So I'm going to start with 0. Oops. Come on. There you go. All right, 0. Okay, so that's 0. 1. That's just 1. 2. You ran out of numbers, so you roll over to 0, go back to 0, and you add 1 in the next column. All right. And 3, add 1. 4, add 1, carry the 1, add 1. carry the 1, get 1, 0, 0. Likewise, you get 1, 0, 1 for 5, 1, 1, 0 for 6, 1, 1, 1 for 7, 1, 0, 0, 0 for 8, and 1, 0, 0, 1 for 9. Now that combination of 10 digits and 10 binary representations is sometimes referred to as BCD, or binary coded decimal. The decimal numbers just represented in binary, as opposed to something we'll get to in just a little bit. But that's how you count in binary. Oops. And this shows you the technical way of looking at it. Each position in a number, regardless of the base, is the first position is that base to the 0th power position, which is ones, the ones position. The second position is the base to the first power position, so 2 to the first power, or 2. The third position is 2 to the second power, or 4's position. How many 4's are in the number, and so on down the line. So each position is a power of 2 in the case of binary. The powers of 2 are kind of important to remember. This takes it up to 2 to the 10th power, which is sometimes referred to as 1K. 2 to the 20th power is 1 meg, and 2 to the 30th is 1 gig. Oops. Now, why that is important is how the number of combinations that you can have with wires is 2 to the number of wires power. So if you have a 32-bit computer with 32-bit addressing, you can address about 4 billion locations and count to, up to 4 billion. The problem is, back in the day when Windows was a 32-bit operating system, if you had a file that was over 4 billion bytes, like a large video file, Windows didn't know what to do with it. It didn't know how to address, 4 billion bytes in one file. It acted a little wonky, and it gave negative numbers for the file size and all that sort of stuff. Now computers are 64-bit, which is approximately huge. Not going to run out of memory anytime soon. No single processor that I'm aware of has that much memory addressed to it directly. So a lot of those addresses go unused. But yeah, not going to run out of memory anytime terribly soon. But memorizing the powers of 2 is helpful for things in computer science and computer engineering. What happened? There we go. Oh, okay. Come on. You're going to be doing me like this all day. All right. So represent this in decimal notation. Remember the powers of 2. You got ones, the ones position. Come on. The ones position, the twos positions, the 4s, 8s, 16s, and 32s. So you have 1 1, 1 4, 1 16, and 1 32. Which is what, 53? I think that's 53, isn't it? Yeah. You get farther along in math and you start forgetting the easy stuff. Anyway, but that's how you convert binary to decimal. So there you go. And then converting decimal to binary, you take the highest power of 2 that's less than the number you're dealing with. So that's 128. Okay? And put a 1 in the 128th position. Okay? And then subtract 128 from 209, gives you 81. Okay, what's the highest power of 2 that's less than 81? 64. So you try to subtract 64 here, and put a 1 in the 64's position. Do a little subtraction. That's 17. There's no 32s. 17 is less than 32. So next one would be 16s. There is a 16 in there, and that's what leaves 1. So there's no 8s, no 4s, no 2s, and there is a 1. So there's the binary notation for 209. Make sense? Okay. You gonna do this to me again? Yes, you are. All right, let's see here. Binary addition and subtraction. Now, we already discussed a little bit about that when we counted up to 9. They are the same as decimal math. You add together. If it goes over if it goes to 2 or over, you put a 0 or a 1 in the case of a 3, and carry the 1. So 1, come on. This thing is not cooperating here. 1, 1, 0, 1, 1, 1, 1. Okay. That's 2, which is 0, 1 is 0, carry the 1. That's 2, that's 0, carry the 1. That's 1, carry the 1. And 2, which is 0, carry the 1, 1. Same as decimal math, just smaller numbers. All right? And this goes through the step-by-step of that. And get that result. Now, subtracting is a little different with binary. They go through it and show it the way you would do it by hand in decimal, where you borrow from the previous column and all that sort of stuff. Computers don't work that way. So the more efficient way of doing it will be covered in a little bit. So I'm going to kind of skip over this. Circuits for computer addition. We'll get back to the subtraction in just a minute. Okay. Consider the question of designing a circuit to produce the sum of 2 binary digits P and Q. Both P and Q can be either 0 or 1. The following facts are known. 1 plus 1 is 10. Argue that with your 5th grade teacher. 1 plus 0 is 1. 0 plus 1 is 1. And 0 plus 0 is 0. But you have 2 digits on your output. So you have to have 2 outputs in your circuit. One is the sum, which is your first digit here. And then the carry, if there is a carry from the operation, carries out to the next column. Okay? So the carry output is 1 if both P and Q are 1. It is 0 otherwise. So that could be represented with an AND gate. The sum output is only 1 if P and Q are different, but if they're the same, it should be 0. Right? If P and Q are the same, the last digit is 0. 0 and 0, 0. 1 and 1, 0. Oh, come on, stop it. Anyway, so that can be done with the exclusive OR operation, or this expression, which we've covered before, is the exclusive OR operation. So, taking that into a circuit, you have P or Q, or not P and Q for the sum, and P and Q for the carry. Okay? That's just one way of implementing what's called a half adder. Because what do you do with the carry? If you have two digits, two binary digits, you have to take into account the carry of the first digit into the second digit, like in this case here. So this is the same as P plus Q plus R. And you create a full adder by doing two half adders. So you add one together, one pair together, and then the result you add with the third digit, the third bit. And you construct it in a circuit using P, Q, and R as inputs. Q and R, I'm sorry, the P and Q, the sum goes to the other half adder. The carry, the two carries go to the OR gate for the carry result, and the sum of from the second half adder is the sum bit. A lot of documentation will call the one of the inputs the carry in bit. So in this situation, we have A0, B0, A1, B1, and A2, B2. So you have two binary numbers, A and B. You send the least significant bits to the half adder. The next corresponding bits to the first full adder, and then the third most significant bits to the final half adder. That'll give you a 4-bit result. Up to 4-bit result. But this is more commonly called a ripple adder, because this result down here is not seen, is not valid until these upper results are valid. The results ripple down the line, and you can string these together, 64 bits wide, whatever. I've never personally ever heard of it called as a parallel adder, but I didn't write the book. But anyway, come on, you're doing it again? No. All right, let's go. Where were we? Okay, 2's complement and computer representation of signed integers. So far with binary, we've only been dealing with positive integers. Negative integers can be represented in binary as well. As I stated earlier, a fixed number of bits is typically used to represent integers on a computer, 32 or 64 bits. The left The leftmost bit, the most significant bit, is usually used to indicate the sign of the integer, whether it's positive or negative. And this method called 2's complements is a method of expressing negative numbers. Okay? For a bit length of 8, for simplicity's sake, we'll look at that. A 8-bit 2's complement integer can be a number between negative 128 and positive 127. For a positive number, the binary representation is the same as regular unsigned numbers. But for a negative number, you have a 2's complement number, which is more easily derived than what they were just showing. By switching all the ones to zeros and all the zeros to ones, or flipping the bits, and then adding 1 to that number. That changes the sign of the number. So, find the 8-bit 2's complement for 46. Okay, well, first, you find the absolute value, the binary representation of the absolute value of 46, negative 46, which is 46. So that's, oops. Come on. I went the wrong direction. Okay. So that's 46 minus 32, which is 14, minus 8 is 6, minus 4 is 2, minus 2 is 0. So you have a 1 in the 32's place, a 1 in a 0 in the 16's place, 1 in the 8's place, 1 in the 4's place, 1 in the 2's place, and a 0. And it's 8-bit, so this is only 6. So we give 2 leading zeros. It doesn't affect the value, right? So what you do is you flip the bits to make it and then you add 1 to it. Let's see here, 1, 1, 0, 1, 0, 1, 1. So that's the 2's complement representation of negative 46. Notice the 1 in the most significant bit position indicates that it's a negative number. A 0 in the most significant bit position indicates that it is not negative. It's either 0 or a positive number. So, did it again. Things would go by much more smoothly if this screen worked properly. All right. Okay. All right. Okay.
What if it's a 6-bit
You typically don't run into 6 bits at a time. You 8-bit, 16, 32, 64, 128, 256, powers of 2. If your number is only uses 6 bits, you give leading zeros to fill up the rest of them. Unless it's negative, in which case you give it leading ones. So if you're come on. If your negative number is this, which is an 8-bit number, and you want to make it a 16-bit number, you just add ones to the front of it. Those two numbers, the previous 8-bit number and this 16-bit number, are the same negative number. No, you don't. When you're adding bits to it, you just add whatever the most significant bit is. Add those to the length.
So, like, when do we flip?
When you're converting from positive to negative. So this is now flip it going upwards. So this is the negative of that. Because I flipped the bits, added 1, and I got that number. And with all these, if these were flipped as well, those would just be leading zeros on the number. See how that works? Okay. Now let's see if we can get back to where we were, if this computer would let me. A long time ago in a galaxy far, far away, I took my first computer class. I was in 7th grade at the time, and I still remember on the wall of that classroom was a sign that said, "To err is human, to really foul things up requires a computer." Stuck with me all these years. Anyway, let's see here. Now the 2's complement, the representations, it's counting up from 0 is like normal binary. Counting below 0, if you take 0 and you subtract 1 from it, it just flips all the bits. So all ones is -1. Subtract 1 from that, you get all ones with a 0 at the end, that's -2. And so on and so forth until you get to -128 for an 8-bit 2's complement negative number. All right. We already went through all this. We can write the decimal representation of an integer with the 2's complement of this number. You flip the bits, I'm going to ask for a new screen in here because this one is not cooperating. All right, let's see here. It's 0, 1, 0, 1, 0, 1. I rest my case. To really foul things up does require a computer. Okay, I'm not gonna. I'll just go through this. Go through the slide. Try not to write on the screen anymore, because that seems to be what is messing it up. Okay, so decimal representation of this integer. Flip the bits, add 1, and then convert it to decimal. And then because you had a leading 1, add a minus sign to it. So you have minus 87. It goes flipping and adding 1 goes both ways. It converts it from negative to positive or from positive to negative. It goes both ways. Addition and subtraction with integers. The beautiful thing about 2's complement negative numbers is you can add them to a positive number and it acts as subtraction. After all, isn't subtraction just adding a negative number? So it works the same way. 2's complement works that way as well. So if you want to subtract a number, say 438 from and subtract 201, you would make the 201 a negative number and then add it to the first number, which makes the circuitry easier because all you need is adders in the computer. You don't need something that borrows from the next column and all that kind of nonsense the way we do it on paper. Computers do it much more efficiently. Convert it to a negative number and then add it to the first number. Yeah, it's going through basically what I was just saying. The only thing that is a little bit wonky about it is sometimes you end up with a stray 1 at the end, on the left. Ignore it. It doesn't mean anything. It's just an artifact. You just throw it away and ignore it, and the result will be correct. Let's see here. General procedure for using 8-bit 2's complement to add 2 integers. Convert integers to their 2's complement representations, add the resulting integers together, and convert the result back to decimal form. General procedure, yeah. Make sure they're in the same notation. If you're dealing with unsigned numbers, do signed math. If you're doing unsigned or signed numbers, make sure they're both signed. Hexadecimal notation, that's base 16. How are we doing on time here? Feels like I got about 9 minutes to cover this. Okay, it's going to be quick. Okay, base 16 works the same way as binary and decimal, only the base is 16 instead of 2 or 10. It's more compact because you can represent numbers with 1 digit from 0 to 15. Hexadecimal digits go from 0, 1, 2, 3, 4 to 9, and then go to letters A, B, C, D, E, and F. A nice thing about hexadecimal is there is a 4-bit binary equivalent. 4 bits is 16 combinations, so there's a 1-to-1 correspondence between hexadecimal digits and the 4-bit binary. Okay, so not going to bother with this. If you want to try it, go for it. Follow the slides and do the calculations, and come to that result. Converting an integer from hexadecimal to binary is just substituting the binary combinations for each hexadecimal digit for those and just stringing them along. So B09F would be 1011000010011111. B09F is a lot shorter and easier to say. But that's a 16-bit number because it's 4 bits for each hexadecimal digit. So there's 4 digits, 16. That's a 16-bit number. All right. So I think that's what I said. But to convert integers written in binary, just do the reverse. Find the combination of bits that correspond to the hexadecimal digits. So converting this to hexadecimal. How many? It's 1, 2, 1, 2, 3. Okay, so it's 4 D A 9. Is that right? Yes. Okay. 4DA9. So you group them in 4 groups of 4 and find the corresponding hexadecimal digit. If there's a not an even number of 4, add leading zeros. Doesn't affect the value. Do the same with that. Oh, the smallest addressable memory unit in most computers is 1 byte or 8 bits. Sometimes you want to get a dump of the memory contents of a computer. The memory locations are, the values are put on the screen, and they're typically done in hexadecimal form, in the form of bytes, which is 2 digits per byte. Now that would be 32 bits. If they represented that in binary, it'd take up half the width of the screen for one number instead of just 8 hexadecimal digits. So it's much more compact and easy to read. That's what those numbers mean in binary, those hexadecimal digits. And that's it. I need to remember not to write on this screen. It doesn't like it. Anyway, that is it for chapter 2. I will have the slides up on the canvas this evening. Sorry I didn't put last session slides up there yet. Slipped my mind. Thursday next week, there will be test number 1. It'll take up the entire class period. It will be covering chapter 1 and chapter 2. So get your notes squared away and ready to go, and We'll have tests on next Thursday. Have a wonderful day.